And yeah, great. So welcome to our next lecture in the Core Systems Development Frameworks. Today we have a special guest. His name is William Lyon. Earlier I had the difficulties to pronounce his last name correctly, but I think I'm getting better at it. And he is with us a second time. And I'm really excited and glad that you're here, and tell us a little bit about neo4j, graph databases, and maybe later on neo4j-graphql-js. So, welcome, Will.
Thanks. Great. Hi, everyone. So I shared a link in the chat to the slides, so hopefully you can access those. What's the best way to take questions? Just in I can see the chat, so folks ask in the chat, I can see that, or if you want to just interrupt me, that's probably fine too. So yeah, so this is kind of the agenda. I'd like to talk a bit about neo4j, sort of an intro to graph databases, and then also talk about how we can use GraphQL with neo4j. So specifically how we can build GraphQL APIs that leverage neo4j as the backing data layer. And we'll kind of go through a few different approaches. Sort of a naive approach for how we might use the client drivers for neo4j to build a GraphQL API ourselves, and then look at some of the problems that come up when we go through that sort of more naive approach, and some of the tooling that exists that makes it easier, more performant tooling that addresses some of those problems that come up. So we'll look at a library called neo4j-graphql-js and a couple of other tools around that. Yeah.
Maybe I can quickly interrupt just to give you a quick background. So we haven't covered databases at all, right? So we are at the GraphQL level, and we are in the next homework, we will going to add persistency to GraphQL. We basically, we didn't cover it at all. So you can also give us maybe a quick introduction what neo4j is and what's the nice thing about a graph database, etc.
Yeah, that's perfect. Great. And what's the time frame, by the way? How long should I yammer on for?
You have 90 minutes. Yeah, just yeah. And I don't know. Students are free to also to leave if you need more. I guess I don't know. I hope people are fine with it.
Okay, cool, great. Yeah, so a little bit about me. Like Robert said, I work at this database company called neo4j, which is an open source graph database, which we'll talk about. I work on a team that we call neo4j Labs, which our goal is to build extensions, plugins, integrations with neo4j and other tooling. So I don't work on the core database itself. Instead, I work on tooling and integrations around the database. I've also been writing a book called Full Stack GraphQL Applications with Grandstack. So that's GraphQL, React, Apollo, and neo4j database. That link in the top corner there is a link to download 3 chapters for free from the book sponsored by neo4j, which focuses on the backend aspects. So maybe a deeper dive of what we're going to talk about today. So what is neo4j is, I think, a good place to start here. So fundamentally, neo4j is a database management system, a DBMS, or commonly just called a database. So if you've heard of tools like Postgres or MongoDB, neo4j is in this similar ecosystem of database tools, DBMSs, where the sort of ultimate goal of a database is to allow you to store and query your data, right? So some persistence, durable persistence layer for your application. And there are lots of different ways to address that persistence problem, and there are also lots of other aspects that come up when you're choosing a database for your application. So things like the performance characteristics for different access patterns. Is it really, really fast to write? Can I shard the database in a cluster? Can I have multiple instances of the database sort of deployed to scale the throughput and the availability of the database? So if one database instance goes down, I have other resilient instances of the database in my cluster. So anyway, these are some of the considerations to think about. The things that I think are most interesting initially when you start working with neo4j are things like the data model and the query language are a bit different with graph databases like neo4j from other database tooling. So we'll talk a bit about those, but that's okay if you're not familiar with other databases. We'll introduce these concepts on their own. So fundamentally, as a graph database, the data model that we work with, so the way that we think about, query, and store our data with neo4j is as a graph. So in a graph, nodes are the entities and they're connected by relationships. And then we can store arbitrary properties, which are the attributes that describe the nodes and relationships. And we'll look at a deeper example of this in a minute, but that's the general idea. We call this the property graph data model because we can store properties on the graph. Now, to work with our data in neo4j, we use a query language called cypher. There's an example here in the upper right corner. And with cypher, so if you've heard of relational databases and SQL, you can think of cypher as sort of the equivalent as SQL or SQL, but for graph databases like neo4j. And the important fundamental aspect when working with cypher is this concept of graph pattern matching. So with cypher, we declaratively draw essentially ASCII art notation to represent graph patterns. So you can see here in this example, we're saying match. So that's basically like find this pattern in the database. And then the thing that follows that match is the pattern that we're looking for. And so starting off, we're saying find address nodes. So nodes are represented in parentheses, sort of like drawing a node is the idea there. And then we have this a:\address. So a becomes a variable that we can then use to refer to the node that matches this piece of the pattern later on. And then :address, so the thing after the colon is called the label. That's just a way to group or describe the nodes. We're saying find address nodes that have now this connection, this registered address. This is drawn with these square brackets and this sort of arrow ASCII art notation that represents a relationship. So a relationship coming into the address that's connected to an officer node within an outgoing relationship to an entity. And here we've left off the type of the relationship. So you can see we can construct these sort of arbitrarily complex patterns. So this is saying find addresses that are connected to an officer node through this registered address relationship, and then find all of the entities connected to that officer. And then we're filtering where the address contains New York. So this is saying find all of these entity nodes that are connected to officers with an address in New York. This query comes from the Panama Papers data set, which was a large-scale data journalism investigation that was looking at offshore legal entities connected to banks and various other people throughout the world. And the group that was investigating that data set used neo4j to model these connections of offshore legal entities, the people connected to them, and where they're located throughout the world, because it's a very complex structure. So that's one of the things that graph databases are really good for, is modeling very complex and connected data. So if you think of like offshore legal entities where you might have a business that's registered in the Cayman Islands that owns another business that's registered in Panama, that owns another business, and then that business owns a plane. You want to be able to sort of traverse this graph to find who's the person who owns the company that owns the company that owns the company that owns the plane, right? So anyway, that's one example of where graphs come in very, very handy for representing this very complex and connected data set. So once you have your data in neo4j, there are lots of interesting things that we can do with it. So we can build applications on top of neo4j, like web applications, which is kind of what we'll talk about today. But there are also lots of interesting use cases for things like graph analytics. So we can run graph algorithms like PageRank or community detection to find clusters or to find the most important nodes in our network for things like recommendations or for search engine optimization, these kinds of things. And then there are use cases for graph visualization tools. So I may want to be able to interpret the results of these algorithms, or I may want to explore the graph using some of these visualization tools. Neo4j is available to download locally, or there's a hosted solution in the cloud. You can deploy it to like AWS, Amazon, or Google Cloud Platform, that sort of thing as well. And then, which we'll talk about a bit later, there's a GraphQL integration as well that makes it more straightforward to build APIs that sit between our client application and the database. So you can think of neo4j and sort of the tooling and use cases around it as a graph platform. So here the database is sort of sitting at the center of this platform, and there's different tooling and use cases depending on what you're trying to accomplish, right? So in our case, we're probably most interested in this upper left quadrant where we're building maybe web applications that are talking to some API layer that we're building. But it's important to also keep in mind that there are other use cases. I mentioned the graph analytics aspect, so more of the data analyst, data scientist use case, where they're maybe not necessarily interested in building a web application, but they're interested in running graph algorithms, maybe part of a machine learning pipeline, these sorts of things. So different use cases and different audiences with different tooling, but the core neo4j property graph model working with Cypher, that sort of remains the same. So we talked a bit about this idea of the property graph model. Here's an example. So here we have 3 nodes, and the caption of the node here, so employee, company, city, that is called the label of the node. And the label is a way to group nodes. It sort of describes what type of node it is. Nodes can have 1 or more label. Here we just have 1. And then we can store arbitrary key value pair properties on the node. So here we have a property with the key name and the value Amy Peters. And we can store things like strings, integers. We can store date, time, representations. We can store geospatial point types, these sorts of things. Now relationships, similar to labels, they have what are called a type relationships have a single relationship type. So whereas nodes can have multiple labels, relationships have a single type and a direction. So you can see there's a direction connecting the company is located in the city. So one way to think of the property graph model is sort of describing a sentence where the nodes are nouns, the relationships connecting our nodes are verbs, and then our properties are like adjectives or adverbs that describe the nodes and relationships. Here's another example. Maybe this one is a bit more concrete. So here we have maybe like the data model for an online store, an e-commerce store, something like that. So we have an order in the middle here. It has an order ID. And then we can see the customer who placed the order. His name's Bob. And then we have an employee who fulfilled the order. So here's an example where we have multiple labels on the nodes. And this is sort of a way to describe a hierarchy almost. So Bob and Amelia are both person nodes. So they both have the person label, but we have a more specific way to describe Bob, and that is as a customer, and Amelia is an employee. So that additional label gives us a greater level of specificity when we're thinking about our data model. So I see a question from Jennifer in the chat. Is there a rule or convention that the relationships need to be in capital letters? Yeah, so that's purely a convention. I think there is a Cypher style guide that describes this convention. Yeah, here we go. I'll drop this link in the chat. So yeah, the convention is for node labels to use this camel case or Pascal case, and relationship types to use all uppercase, and then the style guide also goes into how to think of keywords and working with property names and that sort of thing. So it's fairly opinionated, but those are just conventions, not rules. And it's helpful, I think, to have these sorts of conventions as some sort of standard, so that when you go from maybe looking at the way one user defines this data model and writes their Cypher query, and you go and look at another, you can very quickly make that sort of mental model just looking at the data model, and you see something in all caps that jumps out, yes, relationship type, and that sort of thing. So that's the benefit of that convention, I guess. Yeah, good question. Yeah, and then as Jennifer says, if she tries to return something, match in all lowercase works with just the same as match in uppercase. And yeah, so there's just the convention there of using all uppercase. It's not enforced at all by the database. Yeah, good question. So we're looking at our example here of our store e-commerce property graph model. We talked about this concept of multiple labels on a node. We have a similar concept here for our products. So we have two products that were in this order. What did we buy? Some spaghetti noodles and a book. So the other interesting thing here to point out, I guess, is note that we can store properties on the nodes or the relationships. And so the question comes up, well, when should I store a property on a node versus a relationship? And the answer is if the property is describing just the entity, just the node. So like example here is the SKU or like the ID for the product and the description of the product. Well, that doesn't have anything to do with the order. So that clearly belongs as a property on the node. But then here we have the number of this product that we've placed in the order. So the order contains two packages, whatever, of spaghetti noodles. And that information, the number of products in the order, well, that's not describing just the order or just the product. It's describing the product in the context of the order, right? So that property is describing both the order and product. So that means it belongs as a property on the relationship. Similarly, for the date that this order was fulfilled by this employee, there could have been another employee that was also working to it who maybe fulfilled the order on a different date. That date's specific to both the order and the employee, so it belongs on the relationship. This link down at the bottom, this is a link to a simple graph diagramming tool called Arrows that just runs in the browser and allows us to draw these property graph models. So this is one that I was working with previously, designing the data model for a podcast application. But this just allows us to sort of allows us to sort of draw these models and think about them. One thing that is nice is I can export the markup and then I can take this code that describes the data model and then share that with my collaborators. I can check it into to version control, like on Git or GitHub, something like that, and actually version the data model, which is quite nice. Cool. So if we think of that data model that we've described with customers and employees and orders and products in the order, how do I then work with that using Cypher? Well, here's an example. This query, this pattern that we've built up is a bit more complex than that first example that we were looking at with the Panama Papers data. We're now saying find this pattern where a customer placed an order and that order contains a product, and then find other orders that have that same product where the customer's name is Bob. So this is saying, okay, find Bob, find all the orders that Bob has placed. Now, what products are in those orders? So what products is Bob ordering? And then find other orders that have those same products. And then we have another match, so we traverse out again. So from these orders that have the same products as what Bob is ordering, what products do they contain? And we're binding this product to the variable rec, REC. And we're then filtering with another predicate that says where this recommended product is not the original product. So basically where Bob has not placed an order for this product, and we're going to return rec. So this is a product recommendation query. This is very similar if you're on online shopping, something like Amazon, and you're looking at products and you see these recommendations that say, well, people who bought this product also bought these other products. This is exactly the type of query that's running on the back end to generate those sort of recommendations. So you can see how it's relatively straightforward to define these sort of traversals through the graph, starting at our customer, traversing out to their orders, products, orders that contain those products, and then what other products are people buying that are buying the same thing that Bob is buying, right? This idea of collaborative filtering, I guess, is the terminology to describe this sort of product recommendation traversal. So this sort of personalization, this is a really great example use case where graph databases are commonly used because they're optimized for a couple of things. One, they're optimized for expressing this sort of traversal. So expressing this in Cypher, we draw this sort of ASCII art notation. It's fairly straightforward to reason about how we're traversing through the graph. But then in the database itself, the database is optimized for these sorts of traversals. So every time that the database is traversing from a node to another node that it's connected to through a relationship, that's a very fast operation in a graph database like neo4j, because it's essentially every record essentially has a pointer to an offset on disk is how it's implemented, but it's basically just chasing a pointer to exactly where in the file store that node is represented. Whereas other databases, they may have to do what's called an index operation, where they're taking two large sets of data, seeing where they overlap, and that's sort of the equivalent of this traversal, often called a join operation. So building a database is all about optimizing for different patterns and use cases, and the optimization that graph databases make are on doing these sorts of traversals very, very efficiently, which is different from the optimizations that other databases make. Anyway, so that's just an example of the type of query we might see in a e-commerce application for personalization. So let's talk a little bit about some of the tooling that we might use with neo4j. So the neo4j browser is one of the first tools that you use to interact with neo4j. Typically, you can think of it as a query workbench for neo4j. So it allows us to send Cypher queries to the database and then visualize the results. It's also a nice getting started and educational tool. There's ways that we can embed guided sort of exercises and things like that that allow us to embed queries and text and things like that. And this is sort of the default tool that we initially use to work with neo4j. So let's take a look at an example. So I'm going to switch to neo4j browser. If you want to try this on your own, there's a couple of ways to get started. One, you can download neo4j. The default download is called neo4j desktop, which we'll take a look at in a second. Or there's a online sandbox environment as well that allows you to spin up databases preloaded with data sets. But I'm going to switch to neo4j desktop. While I'm switching into this, are there any questions so far on what we've talked about?
Yeah, maybe what I really like when talking about graph databases is most of the students probably have experience with SQL, table-based databases, and MongoDB, which is a document-oriented database. And I really like to have this mental model in mind that neo4j is a graph database. So it takes the graph as the central data structure. And the other databases are usually also exposing implementation details, for example, foreign keys to the end user, to the developer. And that's a fundamental difference to neo4j, which is hiding this implementation detail. And you can all focus on the structure of your data, right? So also things like a dangling pointer, which is a foreign key in an SQL database pointing to nowhere, this is not possible in Neo4j, right? And I think that's one of the key fundamental differences compared to the databases that most people get in touch with during their, like, I don't know, during university or something.
Yeah, that's a good point. So when we're talking about doing these sorts of traversals from, like customer placed order, if you're doing that in a relational or SQL database, instead of declaratively writing that pattern, you're writing like a SQL join statement and trying to figure out on what foreign key you're joining on that's overlapping from the customer in the order, right? So it's in my mind, I think a bit more straightforward to represent that in a graph database.
Yeah, and also when I was at university, I also had like a little bit of graph theory and graph algorithms. And these people there, they are mathematicians, so they don't even worry about implementations, and they can develop algorithms for abstract graphs, right? And they have this concept of, first of all, a graph, then a directed graph, and then a property graph, a labeled graph, and all of these things. And Neo4j is implementing that. So I'm not 100% sure if graph theory or anything like that is a thing at TW, but these algorithms developed in this abstract mathematical world are applicable at graph databases, right? And that's also one thing to, like a nice connection to keep in mind, I would say.
Yeah, and because you mentioned graph algorithms, there's a very, very interesting project called the Graph Data Science Library for Neo4j, which implements a lot of these algorithms in what are called procedures, but essentially ways that you can use them in Cypher. So things like PageRank, these are centrality algorithms, things like similarity algorithms, community detection. So we won't really dive into too much of this today, but I just want to mention, if you're interested in graph algorithms, that this is a great library to be able to work with these sorts of algorithms in Neo4j. There's also what's called a Pregel API, so that you can also implement your own custom algorithms in Neo4j using this Pregel API. So anyway, yeah, lots of interesting use cases for graph databases for sure.
And there's one question in the chat.
So would you say that graph databases replace table-based databases, or any downside of graph databases? Yeah, that's a really good question. You can fundamentally, I guess you can think of graph databases and relational databases as, or document databases as interchangeable for the, I guess, more common use cases, right? So if I'm building what is commonly called a CRUD application, so if I want to build a web application that has simple create, read, update, delete functionality. So if I'm building like a to-do app is a very common example, where I want to make a list of like all the things that I have to do, and then I want to like edit those, I want to check them off, right? If I'm building something like that, then sure, I can do that in a graph database, I can do that in a relational database, I can do it in a relational database with SQL. They're sort of interchangeable there, and there probably isn't really much advantage to using one type of database over the other in that case. However, when I have more complex applications, or when I have to think about the scale of my application, if I want to be able to support, millions and millions and tens of thousands of concurrent users, if my data model is very complex, if I have complex authorization rules, then the different types of databases, the optimizations and the trade-offs in the implementation of those databases, then they start to make a difference. So I mentioned earlier that graph databases are optimized for these sort of local traversals where I'm going from one node to a connected node to another. And in our product recommendation query, we have 1, 2, 3, 4 sort of hops that we're doing in our traversal. But you could easily imagine a complex query that is maybe 10, 12 hops out. And if you have a complex access pattern like that, where in this case, we're generating product recommendations or personalization, but it could be other things like maybe routing, where I want to find the most efficient path from like the grocery store to the brewery or whatever. That can be much more complex, and a graph database is going to be optimized for that access pattern. We're doing that in a relational database is going to be one, much harder to express in SQL by writing these joins, and like Robert said, thinking about foreign keys and where those overlap, but also the performance aspect in a relational database is going to start to break down because each one of those join operations is using what's called an index. So it's basically taking where two tables, putting them together and using an index to see where those tables overlap. And as I start to have very, very large tables, and as I start to have lots of those join operations in a single query, that starts to get really, really slow. So in a graph database, the performance of a traversal is basically a constant time operation. In computer science, you have this concept of big O, which is basically sort of like how does the performance of the operation scale as the size of the data scales. So that's a constant time operation for a traversal in a graph database, for a join operation in a relational database. It's dependent on the overall size of the data. So as I add more and more rows to my tables, join operations start to slow down. So that's one area where a graph database is going to give us better performance than a relational database. But to your original question, you're asking, okay, well, what are sort of the downsides of a graph database? And every database is sort of this this choice in trade-offs, and the trade-off that we're making perhaps with a graph database is that we're materializing these relationships at write time. So in a relational database, when I make a write operation, I'm adding an entry in a table, adding another row. I'm not storing that relationship in the database at write time, whereas in a graph database, I am. So every relationship is a first-class citizen in the database, and at write time, I'm persisting that relationship. So in a graph database, you may see different performance with regards to write operations than you might expect with a relational database. So that's perhaps one downside or way to think about the access patterns of a graph database differently. Another is when it comes to sharding our data. So if we want to be able to split up our data set into what are called multiple shards, so basically if we have lots and lots of data, so if we have multiple terabytes of data that we can't store on a single machine, we want to be able to shard that and spread it out to multiple machines. And then when our query comes in to our database cluster, we know which database instance to route that to based on what piece of data we're querying. Well, a graph is a very connected structure, and so it's more difficult to shard the graph and to figure out which piece of the graph goes on which machine, because when a query comes in, I don't want to have to incur the network latency to go to a different database instance in my cluster to access a different shard of the graph. You can create shards in neo4j, that's possible, but you have to think about the performance implications then of a query that's going to have to make a network request from one machine to another to do this traversal. So anyway, so yes, there are trade-offs and optimizations for different databases, but it really depends on what type of application you're building and what your access patterns are.
Yeah, maybe I would really like to add that it really depends on your use case. So for example, if you have a use case where all you're interested in is crunching numbers, right? You have a table and all that you're interested in is like building the average on one column or the sum of one column or something. Obviously, that's where a table-based database is better. But I was, for example, working on a project which was a social network, and we're not crunching numbers. We were interested into the structure, right? We had people, we had users, they wrote posts, and they were friends with each other, and they're following each other, and obviously we were interested in the structure, and that's where a graph database really shines, I would say. So it all depends on the use case. I don't think that graph databases will replace table-based databases. Table-based databases have their use case, so do document-oriented databases. It's just that maybe in the last 20 or 30 years or so, it was easier to implement table-based databases, which were performant. And now we have more options, and we can choose the best database for my particular use case. And we should stop thinking in this box that, okay, database is a relational SQL database or something. It's like, I have a plethora of databases which I, as a developer, can choose for my particular use case, right? And I think for me, it's really strange that graph databases are still considered like exotic or something, which, no, actually, for me, they are not, right? Because most of the time, or very often, our use case is about the structure of data or something. Yeah. Well, most of it, yeah, that would be a great use case usually for a graph database, yeah. There's also another question.
For sure. So Marcel says, isn't every node kind of like a table as well? So I think if we go back to maybe this diagram, or maybe this one, which doesn't have multiple labels, because that sort of muddies the water. But yeah, so the way I think about it is, you can think of a node label, so like the employee label, where I'm going to have multiple nodes with the label employee. So one node to represent each employee of a company. A way to think of comparing the label to the table is that, yeah, like the employee label is kind of like a table called employee in a relational database. So a way to group nodes, right? So in this case, representing this in a relational database, I might have an employee table, a company table, a city table, and then for the relationships, well, I might have a join table to join employee on company that has additional attributes that is here storing the start date. So yeah, think of labels as essentially a table or a way to group nodes is a good way to think of it.
Yeah, so you can represent tables as graphs, of course. And I think we are now halfway through, like it's 45 minutes. And yeah, let's maybe continue on, I would say.
Yeah, so I'm gonna jump over to neo4j desktop, and I have some databases loaded here. Let's create a new database just so we can see what this looks like. So this is what the sort of default download of neo4j desktop will look like. You can create projects. Each projects can have multiple databases, and then when I create a new one, let's call this my database. I need to give it a password, and I can either in neo4j desktop, I can either create local databases, which are running on my machine, or I can create remote databases, which allow me to connect to databases that I may be hosting in the cloud somewhere. So like on neo4j's cloud service or neo4j sandbox, or if I've deployed a database somewhere else. And then I'm going to open neo4j browser, which will allow me to write some queries and start working with neo4j. Let's get hung up. Let's try that again. There we go. Make this a little bigger. Okay, so the first thing I'm going to do is, so this database is empty. If I do something like match in, return count in, this query, this is saying just match on every node. So that's what the parentheses mean. I could specify like a label here, but a pattern, a graph pattern can be sort of as specific as I want it to be. So here the in is a variable that's going to be bound to every or any node in the database and returning the result of an aggregation function count that is going to give me the number of nodes. There's 0, so let's add some data. So I mentioned that we have these browser guides. So I can access those by running this :play command, and this pulls in a browser guide that then embeds some queries and text as sort of like educational things, and I can click on these. So this one that I loaded, :play grandstack, this is just a sample data set that I like to use that has data on businesses and reviews. So here we're loading in some data from a CSV file, and we haven't talked about how we create data in the database, but we do it in a very similar way to how we match on data, where we sort of describe the pattern that we want to create. So here, instead of match that we saw before, we're saying merge. Merge is a write operation that avoids creating duplicates. So we could say, this could also say create, and then we're going to create these business nodes, one business node for each row in this CSV file. But we don't want to create duplicates, and we have a business ID field here. So we'll say merge to avoid creating any duplicates. With merge, other databases use the terminology of upsert or create or get, essentially. Like, does this thing exist? If not, create it. If it does exist, then just match on it, essentially. Anyway, so we go through that process, creating businesses, users, reviews, then connecting them together. So if I run this query, it says I've added 36 nodes, set some properties, created some relationships. Now I can say call DB schema visualization, and this will then inspect the data and give me this graph view of the data model. So these are the node labels and relationship types that I have in the database. So I have users that wrote a review, that reviews a business, and businesses are in categories. So now if I write a query, let's find a user and look them up by name. So here we're matching on a user node, and then we're adding in curly braces specific properties that we want to match on as well. So now that becomes part of our graph pattern. So we're saying find a user where the user's name is Will. This is a sort of equivalent to this representation as well. Okay, so here's the Will node. And if I double click on these, I can traverse out and find, okay, here's the reviews that Will wrote. If I traverse out, those reviews are connected to businesses. Here's a review of Kettle House, which is a brewery. So it's in category beer and brewery. If I keep traversing, I can find other businesses and reviews and users that have reviewed those businesses. Jonas says, is b.name something like a key and therefore colored differently? Yeah, so in this case, u is a variable. So we have some syntax highlighting here in this Cypher query editor, where the syntax highlighting is trying to give us some like semantic information with the colors. So u is a variable that refers to any nodes that match this pattern. And so we're coloring u a bit differently than the like Cypher statement commands. Yeah, you say in the initialization script. And yeah, we should see that similar case in the initialization script, where b, after we create this business node, so in this case, we're iterating through this CSV spreadsheet. That's what this load CSV with headers line means, is grab this spreadsheet, the CSV file, and iterate through each row. And then for each row, create a business node. And the b here, that's now a variable. You can see here, though, I think this is what your original question is. So b.name is colored differently from b.city. And yeah, I think that's the simplistic approach of the Cypher editor here, not understanding name, I think, is a Cypher keyword. And it is coloring it differently because it thinks it's a Cypher keyword and not a property. Yeah, so that I think is just a bug in the Cypher editor. A very keen eye, if you notice that. Cool. So we saw here's sort of how we can write a query and then like double click to traverse out and explore the data. But what if we want to write a query that expresses this traversal? We don't want to just like be double clicking here. We can write more complex queries. I think I have a few saved here. Oh, that's for a different one. Let's switch to the browser here. So you'll notice that we have these saved queries in neo4j browser. So if you write a query and then click this favorite button, it'll save it in local storage, but that's only saving it in that browser instance for neo4j browser. So like if I go here to neo4j desktop, I have different queries saved here. This is for a different data set. But anyway, what I want to show is how we can construct these more complex traversals based on that initial sort of predicate that we wrote. So we said, find the user named Will. Now we're just adding more complex traversals to that pattern where we're finding not just the user, but also the reviews that they wrote and what businesses those reviews are connected to just by building up this graph pattern. And you'll notice as I hover or click on these nodes, I can see the property values down here. So this car is Ducky's Car Wash business node. It has an address, business ID, a city, the latitude and longitude, and so on. And then here's a more complex query. This is a business recommendation query. This is very similar to our product recommendation query where we were looking at what products are people buying who buy the same products that I do. This is now applied to businesses. So what businesses is this user Will reviewing? Well, what are other businesses that users who review those same businesses reviewing? Oh no, this is actually looking at categories. What categories are the businesses that I'm reviewing in? What are other businesses in those same categories where I have not reviewed that business? So recommend new businesses to me that are in categories that I'm interested in. And here's a few businesses that this user might be interested in that they haven't reviewed yet based on sort of overlapping categories. So a similar concept to the query we saw before, but I just wanted to show how we can use neo4j browser to send these queries to the database and sort of work with the results. You'll notice here that we also have a table view, and we have both the node that we're returning and a score value here. So the score in this case is the number of paths. So basically the number of like overlapping categories that got me to this recommended node. And we have the graph view as well. So we can return graph objects, so nodes, relationships, paths, or we can return scalars and more tabular data. We can mix those. It's probably more helpful if I just return maybe the name of the business, and then I get sort of tabular data that says, okay, this is the top recommendation. It has a score of 2. Okay, so that is a quick look at neo4j browser and how we can write queries, visualize the results. In most cases, though, we're interested in building an application. So the browser is useful for sort of development where I'm writing queries in the browser and visualizing the results. Typically, we're building an application and we want to query the database from our application code. So this is where the neo4j client drivers come in. There are drivers in lots of different languages. So these are packages, libraries that I can use in my application code that take care of connecting to the database, allow me to send cypher queries, and then serialize the results so I can work with the results of my queries in my application code. This is an example of using the JavaScript driver. Drivers, though, have a similar API and similar concepts where I create a driver instance that has the connection credentials for the database. So it knows how to connect to the database and how to authenticate as a database user. And then when I'm ready to query, it has the concept of session objects. So I instantiate a session from the driver. I have a query. I can send parameters. So here, this is creating a person node, setting the name. I can pass parameters in my application code. And then I get back this result set that I can then iterate through. So the different languages that you're using have similar concepts like drivers, sessions, result sets, but they're idiomatic to the language that you're working with. Okay, so that's sort of a rough overview of neo4j and some of the tooling that we use with neo4j, the property graph model, cypher, and then just a brief look at the client drivers. What we're going to talk about next is how we can build GraphQL APIs using neo4j. So let's take a look, first of all, at sort of why we would do this. There's some benefits, I think, of using GraphQL with graph databases like neo4j, and we'll talk about a few of those, but I think one that stands out is the graph data model. So with GraphQL, we're describing our data model for the application layer as types and how they're connected. And that's building up a graph. If we think of how we represent that data in a graph database, it's very similar. So we have this concept of graphs in our database and graphs in our application logic. GraphQL makes this observation that your application data is a graph. So I think there's a benefit there of having a very similar data model, both in the database and in our application data. So when GraphQL was first open sourced several years ago, this was something that at neo4j we were interested in to see if it made sense. First of all, I guess to use GraphQL with neo4j, so to build GraphQL APIs on top of neo4j. But I mentioned that I work on a team that builds integrations with neo4j and other technologies. So we were very interested in seeing if there was some sort of integrations we could build to make this process of building a GraphQL API on top of neo4j more straightforward, or if we could optimize any part of that process. So we started talking to a lot of users, both in the neo4j community and in the GraphQL community at large, to see sort of what were some of the pain points that they're running into, to try to find opportunities for some sort of integration that we could build. And ultimately, this led to now what we call grandstack, which is this combination of technologies that work together for building full stack applications. So that's GraphQL, React, Apollo, and neo4j database. Grandstack.io has the documentation for this. The most interesting aspect, I think, though, and what we'll talk about today, is the GraphQL neo4j integration piece. So how can we build GraphQL APIs that can talk to, generate queries to fetch data from neo4j? Can we use the GraphQL type system to define the data model in the database? These sorts of things. So if we take a look at sort of what I'll call the standard approach of building a GraphQL service, and I think this is something that you've covered in previous lectures, the standard way to do this is to create your GraphQL type definitions. You can either do this using the GraphQL schema definition language or by constructing your schema programmatically. But fundamentally, you're basically defining the types in the API. So what are the objects, what fields do they have, how they're connected. And then the next step is to implement resolvers. So these are the functions that are actually responsible for fetching data from the data layer. And that can be a database, that can be multiple databases, that can be even connecting to other APIs, any combination of that, right? But the resolvers are the functions that have the actual logic for resolving the GraphQL request. And then we use something like Apollo server to basically attach these resolvers to my type definitions to serve my GraphQL schema so that it can handle incoming network requests, sending a GraphQL query, execute those resolvers, and then send the data back, right? This is the general approach for building a GraphQL service. So we start with GraphQL type definitions. I won't go into too much detail here because I think you've covered this previously, but these type definitions describe, right, all of the data available in the API. They specify the entry points for the API on these special types called the query and mutation types. And again, we can do this using the schema definition language, which is the example we have here, or we can also do this programmatically. Then come the resolvers, and these functions are attached to our schema, so they map to the types in the fields that we've defined in our GraphQL schema. And inside a resolver, we may do things like initialize a connection and a query to a database. We might have to think about enforcing some authorization rules. We can do that elsewhere, maybe in middleware, something like that, but we can also do that inside resolvers. And then we may have to validate or format the response that comes back from our database and then return the results. Each resolver is passed a few arguments. So the first one, or the object argument, this is basically the result of the object that we're currently resolving. And if this is the root resolver, so if this is the query field resolver, this first argument will be undefined because we haven't resolved anything yet. Then we have the parameters argument. These are the field arguments. So if we've passed in any arguments to the current field that we're resolving, those will be available there. This is common if we're maybe doing something like pagination and we have a first or offset parameter, or if we're doing some filtering, something like that. Then we have the context object, and in the context object, we may have things like a connection to the database. So it's common when we're using, say, like, for example, the neo4j drivers that we looked at earlier, to inject a driver instance that has a connection to the database, or maybe we have some other API abstraction layer in the context object. This is useful because then in our resolver function, we can make that connection to the database there. And then the fourth argument, this is one that we may not commonly use in manual implementations of our resolver functions, where we're writing these resolvers by hand, but it's very important for some of the GraphQL integration, some of the tooling for GraphQL that maybe generate data fetching code, and that's the GraphQL resolve info object. And this object has information about the GraphQL schema and the query, the GraphQL query, GraphQL operation really, that I'm currently resolving. Okay, and so this example, this is for a GraphQL API representing conference sessions. So I have sessions that are in a room that have a theme, and then I have recommended sessions. And with using something like an ORM or some API abstraction layer, my resolvers might look something like this, where I have some object in the context that gives me a connection to the database or wherever I'm resolving this data from, the data layer. It doesn't really matter. I just have some abstraction over that. And then I'm using this ORM-like object to make these queries. So I'm saying find sessions by some search string, here grabbing the search string from the parameters passed into the initial query field. Then when I go to resolve the nested data for, in this case, my session object, I'm going back to the database and saying, okay, here's the session that I'm resolving. I grab that from the object, so the session that I've resolved so far, and saying, hey, find the room for this session, look it up by session ID. Same thing for the theme. And then maybe I have some logic for finding recommended sessions, and I need to go back to the data layer again with the session ID to find the recommended sessions. So this is kind of a common pattern where I'm implementing these resolvers and using some ORM-like object to go back to the database. On the left here, this is an example from another API. This is actually from the GraphQL API that powers the neo4j community site. So community.neo4j.com. This is our discourse forum for neo4j, but all of the data from this top part and these feeds, these activity feeds, come from a GraphQL API. And it looks something like what's on the left there, where we have a cypher query and we use the neo4j driver to issue the query, and then we have to format the results that come back a little bit. So we can construct database queries directly in our resolvers, or if we have some other ORM-like object to work with, that's a common abstraction as well. And then we use something like Apollo server to basically serve this executable schema to handle network requests. But there's a few problems from this, what we'll say, naive approach. One is this concept of schema duplication. So we have to maintain a schema for the database and for the API. And then we end up with this sort of mapping and translation layer in our resolvers, where we may be going from like a graph model in our GraphQL API to a different model if we're using something like a relational database or something like that on the back end. We end up writing a lot of boilerplate code. So basically setup for issuing a query, writing the query, manipulating the results. So a lot of just sort of standard data fetching code that can slow us down as developers. And then there's this concept of the N+1 query problem. So in this example, where we are making multiple requests to this database object in each one of our resolvers, that's going to be a round trip to the database. So the overall performance then of a nested GraphQL query that's accessing all of these fields, it's going to be slowed down as it's having to wait for multiple round trips to the database. That's called the N+1 query problem. And there's some performance implications there. So those are things that we'd like to address those problems in a GraphQL integration. So what sort of tooling exists that can address those common problems when we're constructing GraphQL APIs using this sort of this naive approach. And that leads to this class of tooling roughly or loosely called GraphQL engines. So there are a few of these tools, and they work in slightly different ways and address slightly different use cases, but they're fundamentally tools for auto-generating either your GraphQL schema and generating database code or one or the other there. So there's tools for Postgres, some hosted solutions that AWS has, and then what we're going to talk about is the neo4j-GraphQL integration. So if we take those sort of high-level goals based on some of the problems that we run into with this common sort of naive approach of creating a GraphQL API, where we have a lot of boilerplates, that's reducing developer productivity because I have to write a lot of these things from hand, and it's similar data fetching code that we could probably generate. But then also, I want my API to be extensible. I want to be able to add custom logic, and I want to make sure that that I'm addressing best practices for performance. I want my queries to be fast and efficient. So those are the high-level goals that we sort of set out after looking at how people were building GraphQL APIs in general and also with neo4j. So then specifically, that leads to a few features that we wanted in this integration. And the first one is what's loosely called GraphQL first development. And that's the idea that when we're starting our application, we start with defining the GraphQL schema, or at least the GraphQL types. So the GraphQL type definitions then define the API, and they also define the database model. So we don't need to maintain two separate schemas, a schema for the API and a schema for the database. Instead, we're driving both of those from our GraphQL type definitions. We also want to auto-generate these CRUD operations, so create, read, update, delete operations for our API. So if we just define the types, so if we say we have movies are connected to genres and actors and directors. Well, if we have that, then we're going to want to be able to like create movies, create actors, connect them to connect actors to movies. We want to be able to search and filter for movies by title and year and genre, all these sorts of common operations. And we don't want to have to manually add those operations to our schema. Instead, we want to just auto-generate those. So the neo4j GraphQL integrations take care of adding the query and mutation types with entry points for every type that we've defined in our GraphQL type definitions, adding arguments for things like ordering, pagination, complex filtering, and exposing things like the date time and the geospatial types in our schema. So here, for example, we have a movies data set, and we're filtering for zombie comedy movies released after 1994, or movies that star Jesse Eisenberg and are animation. So you can see how we can construct some complex filtering operations here without really having to write much code. This, by the way, if you want to play around with this data set, movies.grandstack.io, that's a hosted GraphQL endpoint that you can use to sort of see how some of this works. Now, we talked a lot about this problem of boilerplate code in our resolvers and having to write a lot of data fetching logic. It would be really nice if we could just generate this data fetching code from GraphQL. So that's a big part of the goal of the neo4j GraphQL integration, is to take arbitrary GraphQL requests and automatically generate cypher queries to resolve those and send those to the database, so that as developers, we don't have to think about that for these simple CRUD operations. But we do want to be able to add custom logic to our schema, and we do that using the cypher directive. So in this case, we basically here are attaching a cypher query that that the developer has written. We're attaching that to a field in the schema to define some custom logic. So in this case, this is going back to our business reviews application, and we have a recommendation query that says, if you're interested in this business, here are some other businesses you might be interested in, looking at users that have reviewed similar businesses. So then that query then basically is bound to this recommended field, adding some custom logic in our schema with Cypher. So there are a few different implementations of the neo4j GraphQL integrations. There's neo4j Graphql-js, there's a Java flavor, and then there's a database plugin. We're probably most interested in the Node.js, the JavaScript version. So again, just to zoom out at a high level, the point of this library is to help build GraphQL APIs that sit between the client and the database. So we're not sort of sending GraphQL directly to the database. GraphQL is not really a database query language. We still have need for that API layer where we want to implement things maybe like authorization or caching. So we don't want to send queries directly to the database, but we do want to make it easier to build this API layer between the database and the clients. You can think of sort of two main areas that neo4j GraphQL is focused on. One is schema augmentation. That's where we're taking the GraphQL type definitions and adding all of the CRUD operations, things like filtering, ordering, and input types for the mutations, things like that. And then the other big area is the GraphQL transpilation, where we're taking a GraphQL request and generating the database queries, in this case, Cypher, to resolve those requests. So I think we have a few minutes left. Let's take a look at some code here so we can see how this works. So this is a link to a code sandbox. If you haven't seen code sandbox before, it basically allows us to run some JavaScript code, either node or client code on someone else's containers in the cloud somewhere. So this is just pointed to a GitHub repo, so you can also see the code there on GitHub, but this will be a good example to look at. So first of all, here are the environment variables for how we can connect to a neo4j instance. This says UK companies because I first set it up for a different project, but this is pointed at a database hosted in the cloud somewhere that has business reviews, so that same data set that we were looking at earlier. And this is just a read-only user, and it's probably not a great idea to check in your database credentials into GitHub, but I wanted to do that for this demo, but this is just a read-only user, so don't worry about being able to make any changes to the database. You won't break anything. Here we have a GraphQL schema. So here we have some type definitions describing users, reviews, businesses, and so on. We have this recommended field that has the cypher directive on it with our custom cypher query. But other than that, we don't have anything, any sort of like custom logic here. But one thing I haven't talked about is this @relation directive. Because the property graph model encodes the relationship type and the direction of a relationship, we need to be able to model that in our GraphQL types as well. So that's one additional thing we want to add to be able to represent our property graph. If we look at index.js here, so what are we doing? Well, we're pulling in this make augmented schema function from neo4j-graphql-js, and we're then pulling in Apollo server, the neo4j JavaScript driver, and then a couple of utility packages as well. We're reading in our environment variables from that .env file we just looked at, and then we're reading the type definitions from our schema.graphql file that we were just looking at, and we pass those to make augmented schema. And that gives us a executable schema object that we can then pass to Apollo server. The other thing we're doing here with Apollo server is injecting our driver instance. So here we create the driver instance using the environment variables to connect to our neo4j database. But injecting that into the context, that means that this driver instance is now available in every resolver in our GraphQL server. And then we serve that with Apollo server. But there are no resolvers here. We haven't written any resolvers. Typically, to generate a executable GraphQL schema, we have to take type defs and resolvers and combine those together. But that's what make augmented schema from neo4j-graphql-js is doing. It's generating those resolvers for us, so we don't have to write those. If we go to our GraphQL API, let's pull this out into a window so we can see that a bit better. If we look at the docs tab, we can see we have query fields that are generated for each of the types that we defined with arguments for filtering, ordering, that sort of thing. And then also mutations for creating, updating, and deleting nodes and relationships. So if we run a GraphQL query, let's simplify that a little bit. Here we're searching for businesses, name, address, and then what category they're in. I get back some data. If I switch back to my code sandbox, and if I look at the logs here, it's gonna be a little hard to read. We're in code sandbox, but it's logging this generated cypher query. So this query is the exact query that we need to resolve this data from the database. So matching on businesses, finding name and address, traversing out to find what category they're in. And then as I add more complex fields in the selection set here, so now I'm adding, okay, find recommended businesses for each one. As I go back and now look at the logs again, I can see here the query that I added as a cypher schema directive is now embedded in the generated cypher query as a sort of subquery. So the benefit here is, one, I didn't have to write any resolvers to get this GraphQL API. I just define my type definitions, and neo4j-graphql-js takes care of generating both the schema, so the entry points for the API, and the resolvers. But then also at query time, I'm generating a single database query for any arbitrary GraphQL request. So I don't have this n+1 query problem where I'm making multiple round trips to the database. Instead, that's all resolved in a single request. Cool, so I think we're out of time. There's a bit more in the slides that we didn't have time to cover that dives into how these GraphQL database integrations work, how they use the resolve info object to generate these database queries. And then there's also a little bit in the slides that talk about some of the low code tooling that's built on top of this core integration. And then some resources for sort of learning more about some of the things we talked about. But that's the basic idea, I think, of neo4j and using the neo4j GraphQL integrations to build GraphQL APIs. Do we have time for any questions, or should we just leave it there, perhaps?
No, of course we have time for questions. Thank you so much, Will. That was amazing, and you can see people are giving virtual claps on the chat. So one of the downsides of a virtual conference is that you cannot hear the clapping unless people are actually unmuting. And most of my students prefer to write their clap in the chat. And yes, of course we have time for questions.
Great.
Okay, I have a question. For the homework, not for this homework, but for, I'm planning on giving a special Christmas homework, which is all optional, but it's all about deployment. Given that students want to use neo4j-graphql-js, is there there's an easy way to deploy neo4j? Maybe there's a managed hosted database which they can use for development and testing purposes?
Yeah, so for the purposes of homework, development, testing, probably the easiest thing to do is use neo4j sandbox. Let's log out here. neo4j.com/sandbox is what I want. I'll link in the chat here. So neo4j sandbox allows you to spin up a neo4j instance. Go through the flow here so you can see what it looks like. But basically, spin up a neo4j instance that is hosted for you. You do need to sign in. The reason that you sign in is because these instances are private to you. So you can spin up, here we can spin up a blank one. You can also spin up one that has existing data sets loaded, and they have those sort of guides that walk you through how to write queries specific to that data model and so on. But if you're sort of building an application, doing some testing, you can create a blank sandbox that has no data in it. And then once this spins up, I can see the connection credentials. So when I'm using the neo4j drivers to create a connection and query it with application code, here we go. this is what I'm going to plug in, this bolt URL. That's the connection string for the database. And then I have username and password here. So this is a really good way, I think, if you're just sort of developing and testing, if you're putting something into production, there are other options like neo4j Aura is the neo4j database as a service. There's also options on AWS and Google, but Sandbox is free. You can create multiple of these too. So I can also spin up like I don't know, the movies data set or whatever. These Sandbox instances are temporary though, is the only downside. So these by default live for 3 days, but then you get a pop-up and you can extend them for another week. So they live for 10 days. If one dies though, just spin another one up as you're working on your homework. And then a question in the chat about connecting from the application. Yeah, and that's, so there's the connection credentials here, but then if you look in the drivers tab, there's also code snippets for using the different language drivers as well. There's one for GraphQL too. That will show you how to spin up a GraphQL API connected to your database, and it also, you can run that on Code Sandbox as well.
Maybe I should add to that I was thinking about the deployment. So Nede, who was asking this question, for local development, it's probably best to use, I don't know, Docker or install it locally or whatever, because you can also run tests and it's isolated from your coworkers. Once you deploy the application to the web and want to show it to your friends and families and so on, maybe it can be really handy to have such a managed database. Many options are possible. You can also install neo4j locally without any problems, or you shouldn't have any problems.
Right, exactly. Yeah, so the sort of default local, if you go to neo4j.com/download, the default is for that neo4j desktop application, which has some benefits. One, that I can manage a bunch of different projects and databases, both locally and connect to remote databases. But one thing we didn't talk about that we have in desktop are these things called graph apps. Graph apps are like single page applications that connect to a database in desktop. So I'm launching this one called GraphQL Architect. It's going to restart because it had a dependency that it has to install. But these graph apps are really neat because there are things like graph visualization. So if I look, here's the graph app tab. If I look at neo4j Bloom, for example, I can visualize my graph and Bloom. Bloom is different from neo4j browser in the sense that it's optimized for exploring your data without writing cypher queries. So it has this sort of natural language way, I guess, of sort of representing patterns in the graph. And so I can work with my data this way as well. Anyway, there's also a tool called GraphQL Architect. It's a graph app that makes it easy to develop and query my GraphQL APIs locally in desktop without writing any code. So I can generate these type definitions. These were generated automatically from the database when I started this application up, and then I can sort of edit this if I want to add my like custom fields here with like cypher directives and whatnot, and then I can query them using GraphQL, and I can export this to a GitHub project and so on. So anyway, so that's one benefit of using neo4j Desktop, is that it has all of these cool graph apps that I can install that give me different functionality.
All right, nice. Any more questions? It doesn't look like it, so we have a small overtime, but I think this is okay for now. I'm going to take the presenter for some minutes just to show the homework, which is going to start today. So thank you again, Will. And you can stay with us if you want. Actually, it would be great if we can also answer some questions about which came up. Maybe you're even interested in like how our homework looks like. So
I'm very interested in what the homework is. I'm curious if I could pass it.
So we have this homework repository, and it's the 5th exercise for today. You can see the deadline is way in the future, so you have more than 2 weeks. That's because of the Christmas holidays. If you want, you can ask our mentors, that is Yuri and I, for feedback review, so we can give you intermediate feedback on your pull request. And this time it's about basically adding persistency to GraphQL. And so far in exercises 1, 2, 3, 4, you were working with Apollo server and basically just hold the data in memory. If your server stops, then the data is gone. Now, those mutations will write data into the database, and it stays persisted. And the whole goal of this is first of all, the data is persisted, but also your software tests should stay autonomous and should not have side effects. That is, if you write data in the database, you should delete the data or even consider to mock the actual database call. Second, you should make sure that the database is not left in some invalid state. So if you, for example, have I don't know, if you need to set up data in multiple mutations, just make sure that it's not possible to leave, for example, write a post and not have the author associated with it, and these things. And my question to you, Will, is Yuri made me notice that in the lecture I was talking about software tests that have side effects as non-atomic software tests. Apparently there's a conflicting definition of non-atomic software tests. So I was looking at, I think, at this blog post where they were like talking about order independent, causing no side effects, but there's also another one by Source Labs, and they call this autonomous tests, and they use atomic for something else. So autonomous is what atomic is according to the definition of the other blog post. And here they say atomic is you cannot subdivide those tests anymore. Like there's just testing one thing. And I would be interested, Will, do you know the problem, or do you know what I'm referring to? And do you know if there's an unambiguous term for that? Or which one do you prefer?
Yeah, I mean, I think trying to think of how I've referred to these things. I mean, there are two distinct problems here that you're pointing out, right? Like when you have a test suite, and especially for unit tests, you want them to run very, very fast, right? Because oftentimes you want to be able to run your unit tests as you make code changes, and you don't want to wait like 5 minutes or something like that for your tests, especially the unit tests, to finish. So oftentimes you want these tests to run in parallel, right? And so that's where I guess that one blog post was referring to autonomous, so you don't want the order to be dependent, right? So there should be no side effects in your test that then another test depends upon. So like if you have a test that makes a change in maybe like a database, you don't want then a test following that one to be dependent on that change. You want to be able to run all of these tests in parallel. And in my mind, like the main benefit of being able to run your tests in parallel and not having them run serially one after the other is speed, because as I'm writing code, I want to be able to run my unit tests several times as I'm making changes. I don't want to wait and sort of like get sucked into looking at Twitter as I'm waiting for my my test suite to run or something like that. So I think that's definitely one aspect. And then the atomic aspect, which is that I want to be only testing one thing in a test. I don't want to have a test fail. And let's say it's in our GraphQL example, maybe it's testing like, I want to test ordering so that I'm ordering results by some key. I don't want to test ordering and filtering in the same test necessarily, because if that test fails, it's going to take me more time to figure out, well, is it ordering that's broken? Is it filtering that's broken? That sort of thing. So yeah, I mean, I think those are two important aspects, and I guess maybe distinct things. I don't know. In my mind, I'm not usually so concerned about the terminology. I'm more just concerned about the concepts, I guess. But yeah, I think both of those are valid.
Yeah, you're bringing something up which is really important, because I'm mentioning in the exercises that you have two options. That is, if you run the test and those tests will write data into the database, you should make sure you clean the database, or you can consider not writing any data by mocking the response of the database. This obviously will also increase the speed of your test, and you get parallelization, because you don't have to run those tests in succession and wait for the first test to be finished and then run the second test. You can like run all of them in parallel because they don't write data into the database. This is another advantage. Yeah, awesome. Yeah, I was like, I wanted to bring that up because I was talking about in the lecture about it, and wasn't so 100% sure if I'm actually using the right words. Great. So basically, everything should stay feature-wise. Like in exercise 4, we have in exercise 4, I defined a particular schema that needs to be implemented, and we just had like a post and a user object. So we are like implementing something like Hacker News, and users can write a post and they can upvote things, right? So you have this write and upvote mutation, and this should stay the same. And my idea was like, for the persistency thing, that, I mean, there are so many ways to add persistency to GraphQL. It can, as you saw in Will's lecture, the traditional approach would be to have some data source. There's even this pattern in Apollo server, data sources, which you can put into your context and then call in your resolvers, leading sometimes to n+1 problem, of course. And there's so many ways, right? So yeah, I mean, you have even data sources for particular databases, and we could have focused on that, or how to write, how to wrap a REST API with your GraphQL, right? So this is like a very common problem that you will face if you have a legacy REST API, right? But so Yuri and I, we decided, okay, let's focus on a particular advanced feature, which is not something that you would come across immediately when you start writing with GraphQL, but which is really interesting and versatile, and that is GraphQL schema stitching and schema delegation. And we decided to give you two options. So schema delegation traditionally works that you have somewhere in the internet an existing GraphQL API, and you augment this GraphQL API with your own resolvers. So you can feel free to use remote GraphQL API by some headless CMS, for example. I have experience with GraphCMS, which is exposing a GraphQL endpoint. You just basically put your own code in front of it. That is without neo4j, right? So this is my experience from last semester was that some students feel uncomfortable or feel overwhelmed with the complexity of neo4j. So this is also something for you if you, if you're like that. I guess it's a little bit easier for the homework, but what we were covering in the lecture is neo4j. Whoa, that was one click too many. And there's also, as you saw, many ways how to do that. I would suggest you should write cypher just for fun, because you want to learn this query language from graph databases. So you can use neo4j driver yourself, play around with Cypher a little bit and see what are my options, how the Cypher differ from SQL and so on. I also mentioned neo4j, which is like the OR mapper equivalent for graph databases. So OG mapper, you don't have to use it, you're free to use it. And also someone created this pull request at neo4j-graphql-js how to use schema stitching. And you can find code how to set that up for neo4j. Right, so if you want, feel free to check this code out and play with it. Here you can see, I mean, this is, yeah, I think the most important part is probably where we call neo4j-graphql-js. So this is how the resolvers would look like. So you can use delegate to schema and delegate your calls to neo4j-graphql-js. There's also, there's also already existing tests for it. And this is probably one of the most interesting parts where we use neo4j-graphql-js and put our own code in front of it. So you can check that out as a demo code. It's supposed to give you a nice and convenient setup, so you don't have to worry about wiring everything up. There's also demo code for the other architecture, let's say, and this is just a branch in the same repository. So this is the demo branch, and this is explanation how you would use a remote GraphQL API and use the same technique. You can also use schema delegation for that. And but here you have to do a little bit more manual work. Like you have to sign up somewhere and create the schema. You would get a UI and click your schema. And yeah, so I added some screenshots where you can, how the schema looks like, and then you get this API endpoint plus token, which you will need to connect your own Apollo server with this. So this is about the homework. Yeah, some optional tasks if you want. And yeah, Yuri, do you think I should bring up anything else? Maybe Git, yeah, Yuri?
I think, yeah, you described Git crypt. Maybe you can say one or two words regarding that, but I think in general, students need time to have a look at the homework themselves sooner or later.
Yeah, so I was, you saw, Will was talking about it's not the best idea to put credential into the repository. And it's funny because I made that an objective. So in case you have API keys, right, then put them into an encrypted file, and you can use Git crypt for it. It works that you basically rebase on the last homework main branch. And in this branch, we have, let me see. I'm going to click on that and go to the previous commit. No, I think I need to click on commits, right? Yeah, this is the list of commits. So this is the commit where I added an encrypted file, which you can see here. It's like a binary file. But if you put your Git crypt key, which I added to our Moodle course, in a particular location, then you can encrypt those. You can decrypt those encrypted files, right? So download the Moodle, the Git crypt key from Moodle, put it according to the homework instruction at the location, and then run a particular command. Then you should be able to read this file. And if you want to add your own encrypted files, because you have a file with like a .env file and you want to encrypt that, you would just add it to this here. You just specify the location. So this file is at the root level. It's called .hello encrypted world, and you have to add those parameters here, and that's it, right? If you do that first, add then your files, then they get encrypted. To you, it looks like unencrypted, so you can, on your local machine, you can see it, but when you commit it and when you push it, those encrypted files should show up as binary files. All right? That makes sense? You have to do that only if you have API keys. If you if you end up with an implementation which doesn't need API keys, fine. That's probably the best then. Then you don't have to worry about it. Right? Is it understandable so far? Like any questions regarding homework? Silence. People are writing into the chat, so I'm giving a little bit more time. I have to read through the instructions first. Oh yeah, sure. After the lecture, we usually have live pair programming with every group. So you and I, the mentors, are going vice versa and help everyone and like carry out the homework. Just for you, Will, because you might be interested if the thing happens. Well, so, I mean, if there are no questions, I would say, okay, someone is writing. Do you have any questions, Will?
No, that looks like a good assignment. I was thinking of different ways I could go about implementing that. I'm glad you mentioned the git crypt example. I wasn't familiar with that one. I've seen other sort of ways of managing secrets, but that one looks pretty straightforward. Looks quite nice.
Well. If that's it, I would say let's call it a day. And thank you again so much, Will, for this amazing talk. I hope more people feel more comfortable now using graph databases in a real production-ready application. And yeah, it was amazing. I really enjoyed it. Thank you so much.
Cool. Thanks for having me. Thanks everyone for coming.
Great. So we'll see each other in the seminar. Yeah, people are saying thank you. Right, cool. And I'm going to stop the recording, and I can see at some point my computer crashed or OBS crashed, and it wasn't recorded fully.
I think I got it.
Yeah, that's great. It happened to me last time as well. Like I didn't touch my keyboard, it didn't do anything. In OBS, I can see in the icon, it's not recording. So when
Thank you very much, everyone. See you in the exercises, I guess.
Yes. Goodbye.
Cheers, folks.
Thank you again, Will.